Okay, we are live. So, hello everyone, and welcome to another session of the Latin American webinars on physics. I'm Joel Jones from the PUCP in Peru, and I'll be your host today. This is webinar number 163, and we're having Will Thompson as a speaker. Will did his PhD at Yale and is now a postdoc at Harvard University in the USA. Today, we'll present the TAMBO experiment, an intriguing proposal with the objective of observing astrophysical tau neutrinos. We're very happy to have him as a speaker. And before we begin, let me remind all viewers that, as usual, you can ask questions and make comments via the YouTube live chat system, and then the questions will be passed on to Will at the end of the talk. Okay, so we're all yours. Will, please go ahead.
Great, thank you. Let me just share my screen. Hide this thing. All right, how does this look? Good?
Yeah, everything works.
Okay, perfect. Yeah, well, thank you for the introduction and also for the kind invitation to speak here today. So today I'm going to talk to you about TAMBO, which is a proposal for a new neutrino telescope that would be based in the Peruvian Andes, looking for astrophysical tau neutrinos. So today, what I'm going to talk to you about, I guess in detail for TAMBO, is I'll give a little bit of introduction to neutrino astrophysics and use that to directly motivate TAMBO. And then I'll go a little bit more into the details of the TAMBO experiment itself. First, though, I wanted to start off with actually a historical analogy having to do with the discovery of the planet Neptune. So maybe you've heard the story before, but the way that it generally goes is that there's this French astronomer who was observing the motion of the planet Uranus, and he noticed that its motion was actually sort of perturbed in a way that suggested that there is an eighth as yet undiscovered planet that was changing its motion. And so based off these observations, he was actually able to predict exactly where this eighth planet should be. He went down to his local observatory, I guess because this is something that you could do at the time then, and asked them to point their telescope, which is actually this telescope shown on the picture, at this particular point on the sky. And after only one night of observation, they were actually able to discover the planet Neptune. And so I think sort of the upshot of the story is that it's not as if this technology here was not good enough to discover the planet Neptune. It's just that the sky is so vast that they didn't know a priori where they should be looking. As soon as they knew exactly where to look for Neptune, they were able to discover it very quickly. And I see that this sort of role is kind of analogous to the role that I see TAMBO playing in the field of neutrino astrophysics, which is namely to say that essentially we'll be providing a very, very pure set of astrophysical neutrinos and their locations on the sky. This will allow experiments, other neutrino telescopes like IceCube, to follow up and look at these specific points on the sky, which will greatly enhance our sensitivity to discovering new sources of astrophysical tau neutrinos or astrophysical neutrinos in general. Yes, that's sort of the overview. To go into a little bit more details of the outline today. So as I mentioned, I'll start by giving a brief introduction to neutrino astronomy. This will focus mainly on IceCube since IceCube has made a lot of the major discoveries. I also work on IceCube, so self-promotion is always a good thing. Then I'll move on to some open questions which have been raised and are as yet unanswered by IceCube. And this is going to directly motivate an overview of TAMBO, and I'll give an overview of the experiment as well as the simulation that we've been working on. And then lastly, I'll talk about what we're actually doing to realize the TAMBO experiment. Yeah, so to start out, I sort of just want to talk about why neutrino astronomy. Light is like very nice to work with. It's easy to detect. Why would we want to do something as difficult as astronomy with a particle as difficult to work with as the neutrino? Well, it turns out that the neutrinos actually have a few properties that make them very nice to use as astrophysical probes. So first is the fact that they're very weakly interacting, and then the second is that they're electrically neutral. And so let's look for a counterexample first of all. Let's look at photons. So if you want to do something like look at the galactic center in photons, which is something if you live in the southern hemisphere you can actually do. Unfortunately, the Earth is tilted the wrong way in the northern hemisphere. But if you're in the southern hemisphere, you can look right towards the galactic center. But instead of seeing the galactic center, you'll see sort of this cloud of dust which surrounds it. And the reason for this is that these photons or gamma rays really readily scatter off dust. And so instead, what you're going to see is the dust and gas instead of the center of the galaxy. Now, note that neutrinos, since they're so weakly interacting, actually don't have this issue. They're able to pass unimpeded through this hot gas and dust in order to reach us here on Earth. So it serves as a very nice probe through sort of these dusty or dense environments. We can also do astrophysics with cosmic rays, but a difficulty with cosmic rays is the fact that they're charged means that they actually don't point directly back to their sources. This is not the case with neutrinos. Neutrinos are, of course, neutral particles, and so they're going to point directly back to their source. So it's sort of these two features that make them nice to use as astrophysical probes. It's the fact that they pass through dense areas of space unimpeded and are not bent by magnetic fields, so they have this pointing ability. Now, of course, there's a downside here. This very low cross-section means that it's actually very difficult to detect neutrinos, and so we have to create these enormous, enormous detectors to have any hope of detecting even a single neutrino. The situation is actually a little bit worse than that, though. So you might be familiar with some of these experiments that have been looking for, or which have observed solar neutrinos and have really made a lot of fundamental discoveries in the field of neutrino physics. But if you look at the flux of these solar neutrinos, which is in this sort of goldenrod color, I'll call it, and you compare that to the pink flux here, which is from astrophysical neutrinos, you see that the flux of solar neutrinos is something like 30 orders of magnitude higher than the flux of astrophysical neutrinos. And so it's not just this extremely small cross section that makes it difficult, it's also the fact that the flux of these astrophysical neutrinos is just so extremely small. And so what this means is if you want to do neutrino astrophysics, if you want to think of ideas for neutrino telescopes, what you very quickly find yourself doing is sort of trying to think of clever ways to instrument the natural environment in the natural world to serve as your neutrino detector. The reason for this is just that the scale of the detector that you need is so large that you can't really approach it from a civil engineering perspective. You can't build like a scaled up version of Super K or Hyper K that is really large enough to do this. It's just too big. Instead, you have to look for kind of features in the natural environment and figure out clever ways to use them as your neutrino detector. And so maybe the most famous example of this is the IceCube neutrino telescope. So IceCube is a neutrino observatory that's located at the South Pole, if you're not familiar. The basic idea behind IceCube is that so all the time there are neutrinos that are passing through this glacial ice down here at the South Pole. Of course, most of the time, the neutrinos are not going to interact with the ice, but every once in a while we do get lucky. The neutrino will interact with the ice and it will give off a flash of light indicating the presence and some of the characteristics of the neutrino. And so this ice, this glacier serves as our time. And so now all that we have to do is we have to figure out a way to instrument this glacier with photosensors in order to detect these neutrino interactions. That's of course where the real difficulty comes in. So we've drilled down 86 columns into the ice and deployed photodetectors down there in this sort of cubic kilometer volume to create this extremely large neutrino telescope. And so what we get from that, I'm going to show you on this next slide. So I'm going to do something slightly dangerous, which is to attempt to show a video on a Zoom call, which is also apparently being broadcast on YouTube. So we'll see if this works. But what we have here is we have a neutrino that comes in from outer space. It passes through the detector, not interacting. All of a sudden, it will undergo a charge current interaction to create a muon, which the charged particle and will give off Cherenkov light as it passes through the rest of our detector. And so what we're seeing here is one of the kind of typical IceCube event displays. So each one of these spheres represents a photodetector within IceCube. The color of the spheres actually represent the time of the first photon, the time the first photon was seen by each of these photosensors. So events that are more red or sort of yellow colored are earlier on, and events which are later are more blue-green in color. And so what you can see just from this color scale is that our muon started up here and progressed to the bottom right of the detector. And so we can use this to point back to where the neutrino came from to see what point on the sky that it came from. Additionally, we can also see the volume of the sphere here represents the amount of light, the number of photons that each of our photodetectors saw. And essentially the amount of light that we see from these interactions is a proxy for the energy of the original neutrino. So IceCube can measure the energy of the original neutrino, and it can also measure the point on the sky from which they came from. And just to emphasize this again, I'm not sure if you've been to Boston, but this is an image of the Boston Common, which is sort of like the central public park, the public park in downtown Boston. But you can see these events span over multiple city blocks, and are like as tall as skyscrapers. So these are really, really enormous events, really enormous detector. And so if you build a detector that's kind of this large, you're sort of bound to see something interesting, I think. Unfortunately, IceCube has actually seen a lot of things interesting, and it's really made all the fundamental discoveries in the field of neutrino astrophysics. So the first here is just the discovery of a diffuse flux of astrophysical neutrinos, the observation of any astrophysical neutrinos at all. So unfortunately, you can't look at a single neutrino which comes into your detector and determine whether or not this is of astrophysical origin or if it's one of our backgrounds, primarily from atmospheric cosmic rays that produce neutrinos. So instead, this is sort of a statistical measurement that you have to do. So the red histogram here represents our background. You can see at lower energies, we're really, really background dominated by several orders of magnitude over this green spectrum, which is our astrophysical target that we're trying to measure. And so at about 100 TeV, though, there's this crossover where the astrophysical neutrinos begin to dominate over the atmospherics. And so it's the fact that we see the data sort of following out this pink, or I guess we'll call it magenta line here, instead of falling down with the red line that represents this observation of astrophysical neutrinos. So then that we've actually discovered these neutrinos, something we want to do more is characterize exactly what this diffuse flux looks like. This is sort of shown over here on the right plot, looking at a few different models of the energy spectrum. I'll come back to this a little bit later on in the talk. Okay, so we've seen this diffuse spectrum of neutrinos, which basically means that we can say that the sky kind of glows in neutrinos. There's just this overall glow that we observe. But we can say more than that, we've actually discovered point sources of neutrinos on the sky. So this plot over here on the left is showing the northern hemisphere. And the color scale, you can essentially think of, it's essentially just the excess of neutrinos above background. And so here you can see 3 of the neutrino sources that we've observed. The most significant is NGC 1068 right here. And another way to look at this is if you sort of focus right on NGC 1068, you see a peak of events as shown over here. And then as you look further and further away from directly at NGC 1068, the number of events you see falls off, which is exactly what you would expect to see from a point source of neutrinos. And so at this point, IceCube has seen 3 or 4 of these point sources of astrophysical neutrinos. Right, so I mentioned earlier that IceCube can measure the energy and also the point on the sky that these neutrinos come from. We can also actually measure the flavor or an approximation of the flavor of these incoming neutrinos. The way that this works is that different flavors of neutrinos will actually produce different event shapes or different event morphologies within our detector. And the 3 categories I'm showing sort of right here on this slide. So in your track events, these are going to be caused by charge current nu mu interactions. So essentially you have a neutrino, which undergoes a charge current interaction to create a muon. This muon then travels in a straight line through your detector and creates sort of the straight track of light that you can see. These are very distinctive events with an IceCube. In contrast, you can have cascades also, which are caused by charged current nu-e interactions and also neutral current interactions of all flavors. This sort of just creates a blob of light within the detector. And then lastly, you have these double cascades, which are caused by charged current nu-tau events. And so the idea here is that you have this original charge current interaction that gives you your first cascade. You have your tau lepton, which travels out only a relatively short distance because it's so massive, and then decays to create a second cascade. And that's what gives you this double cascade signature here. And so with this, we can actually identify different flavors of neutrinos interacting in our detector. So why might you want to do this? There are kind of a few reasons. So first is that flavor ratios can actually be used to characterize the physics that go on at these astrophysical sources where the neutrinos are created. You can also use the neutrinos from these sources to do sort of as probes of beyond the standard model physics on very, very long baselines. So for example, NGC 1068 is like over 1 million light years away from us, so that's a much longer baseline than you might have from any sort of terrestrial neutrino experiment. So we've made these measurements in IceCube of the overall flavor ratio of the neutrino flavors within the diffuse flux, and the result is summarized here in this triangle plot. This can be a little bit confusing to read because there's admittedly actually kind of a degeneracy here. There's 2 equally good ways to read the plot. You just have to know the convention. So I'll walk through this quickly. So each of these axes represent a fraction of different neutrino flavors. And what you do is you look at the number here, and you sort of trace down along the line that the number is kind of sitting on or oriented with. So for example, if you want to read off the value of this best fit point here, this is going to be 0.3 nu e fraction, 0.5 nu mu fraction, and then 0.2 nu tau fraction, which adds up to 1, which is good, as it should. So the contours are the limits set on this flavor ratio by IceCube, are shown here as this black line or the gray line. But what I want you to notice here is the fact that if you look along the nu mu axis, this contour is sort of very squeezed. It means that we're doing a good job of really identifying the nu mu fraction. But if you look along the nu tau axis or the nu e axis, you can see that the contour is sort of more stretched out. And that's because we're not doing as good of a job as constraining the nu e and nu tau fraction. And this is something we'd like to improve on going forwards. Okay, yeah, so given the sort of successes of IceCube, it's not really surprising that there are actually a number of IceCube style detectors, which are either under construction or sort of in the planning phases right now. And so I'll point out just a few of these here. So first you have P1, which is going to be deployed in the Pacific Ocean, just off the western coast of Canada. It's currently sort of in the R&D stage. CAM3net will be deployed in the Mediterranean. It's actually currently being constructed and deployed right now. And then IceCube Gen 2 will be a future experiment located also at the South Pole, essentially a larger version of IceCube. And so this is going to be very nice for us because, more neutrino telescopes just means that we'll see more astrophysical neutrinos overall. But there's actually a little bit more of a synergistic benefit than just that. And so remember earlier in the talk, I was showing you this plot of how IceCube can see the northern hemisphere sky in neutrinos. So this is actually only true for some energies. At higher energies, IceCube can only see a band of the northern hemisphere. And this band is actually shown right here around the equator. So this is going to be true for all these IceCube style telescopes. And so what all these bands on this plot show are the different regions of the neutrino sky that all these different telescopes are sensitive to. And so what you can see here is that if you just have one sort of giant neutrinos telescope at one place on Earth, you can only see a small fraction of the neutrino sky. But if you have multiple telescopes all over the Earth, you can access a much wider view of the sky and neutrinos, which I think is sort of inherently desirable. Okay, so there is sort of a drawback here, though, which is that all of these experiments that are shown on this plot kind of use, I guess also the sort of IceCube-like detectors. They're these arrays of photodetectors in ice or in water. And so there are some open questions that have been raised by IceCube, which, frankly, it's going to be difficult for these experiments to answer just because they're sort of very similar to the IceCube method of detecting neutrinos. And something that we would like to do is we would like to design sort of a new detector technology to allow us to answer some of the open questions that have been posed by IceCube. Right. So now that I talked about IceCube, I'm going to talk about some of the open questions that are, I guess, left for us that we would like to address that IceCube has posed. Yeah. So for the first of these questions is the nature of this actual diffuse flux of neutrinos, particularly what happens at high energies. Does the flux of neutrinos sort of continue up to higher energies, or is there sort of a cutoff here as is shown in the orange and the green spectra? So oftentimes when characterizing this diffuse flux of neutrinos, we kind of assume that its energy spectrum follows this simple single power law-like behavior. The reason that we do this is because cosmic rays are known to follow a roughly power law-like behavior. And since neutrinos and cosmic rays are thought to originate from the same sources, it kind of makes sense that they're going to have similar energy spectra. Something I'll point out, though, is that more recently, IceCube has actually seen slight evidence for more exotic shapes at about 2 sigma. So instead of seeing this blue single power law, we see some of these spectra that kind of cut off at higher energies. And now this is by no means a discovery, it's only at about 2 sigma, but it sort of just indicates that we're still really trying to get a handle on exactly what this diffuse spectrum looks like. And in particular, it's very hard for IceCube to probe these very high energies above a few PeV just because the event rate up here is so small. And something we really like to get better at is detecting these higher energy neutrinos so that we can characterize if this flux continues or if there is a cutoff at these higher energies. So something else that we'd like to do is we'd like to measure these astrophysical flavor ratios. So as I mentioned before, this is sort of desirable because they probe source characteristics, and they also let you do BSM physics on long baselines. What I didn't mention before, though, is it's kind of difficult actually for IceCube style detectors to distinguish between nu E and nu tau neutrinos. And you might be wondering now, okay, well, how can this be? I can see this very clear double cascade signature here. But what I didn't tell you is that this double cascade here is at 10 PeV. That means the flux is going to be very low for these type of events, and they're going to be very, very rare if they are observable in IceCube. In fact, what typically happens is that if we see these nu tau interactions, they'll be lower energy. What that means is the tau lepton will travel less distance, so these cascades will be not as well spaced apart. And actually, the two cascades will actually kind of start to overlap one another. And so we won't be able to tell the difference between a single cascade from an electron neutrino and the double cascade from the tau neutrino. And in fact, what I didn't mention earlier, this is actually the only event that's not from data of the ones I showed you before. This is from simulation, just because events like this are so rare. And something we'd like to get better at then is, I guess, developing new methods to distinguish tau neutrinos from electron neutrinos. And then the last open question I'll bring up is, where are all these neutrino sources that we should be seeing? I think this is kind of overshadowed right now by the fact that we've discovered the neutrino sources that we have. We see infinitely more than we did just a few years ago. So the fact that we see any at all is nice. But if you look at sort of the flux as a function of energy of both the point sources and the overall diffuse flux, what you see is that there's really this huge gap between the number of neutrinos we see from these point sources and also from the diffuse flux. So where are all the sources that are making up this gap between the point sources that we see and the overall diffuse flux? What is really creating all these neutrinos in the diffuse flux? And something I kind of think is interesting is that this problem is, in a sense, a purely statistical problem. So one way that you can search for sources of neutrinos in the northern hemisphere is you can do a scan over this entire sky map here. And this is actually something that IceCube has done. When you do this, you actually identify NGC at a significance of above 5 sigma, which is enough, of course, to claim a discovery. However, once you take into account this trials factor, which comes from the fact that you scanned over the entire sky, the significance reduces to something more like 2 sigma, which is really not significant enough to say anything at all. So instead, what we've done is we can, I guess, do this analysis in a slightly separate way, which is that we actually can get a catalog of sources and their locations and only look at those specific locations on the sky. Most of these locations correspond with the location of gamma ray emitters. And so this catalog contains only about 100 points, and so that really reduces the impact of this trials factor. So when you use this approach, you instead see NGC 1068 at a significance of above 4 sigma. But really, I just want to point out here, the upshot is that if it weren't for using this catalog of sources, IceCube to this day still would not be seeing any point sources of these neutrinos, as many as we see. And then I'll also point out the fact that this catalog is, in a sense, kind of intrinsically biased because of the fact that we're looking at these sort of structures that are strong gamma ray emitters. And this means that we're biased towards looking for structures that emit gamma rays. Maybe there are some sort of astrophysical objects which are very dim in gamma rays but are very bright in neutrinos. Any of those we're going to be missing out on with this sort of analysis. So we'd like to get better at identifying these point sources of neutrinos. Yeah, so to summarize, what we'd like to do is look for this to see if there's this high energy cutoff. We'd like to get better at identifying tau neutrinos, and we would like to get better at identifying point sources of neutrinos. Okay, so for these ideas, we're certainly not really short on ideas for new neutrino telescopes. This is kind of summarized in this plot over here on the left. What this is looking at is the neutrino flux on the y-axis as a function of neutrino energy. And so one thing that you can kind of immediately observe is that the community has really heeded this call for new ultra-high energy neutrino observatories, which are shown up here. So solid lines represent limits from existing or previous experiments, and then dotted lines like this represent sensitivities of proposed experiments. So you're going to have these ultra-high energy neutrino telescopes up here. You're going to have high energy neutrino telescopes like IceCube down here. This is also where P1 and KM3 net and things like Baikal will be. And something that I kind of want to point out here is, well, one thing, IceCube is the only experiment on this plot which has actually observed astrophysical neutrinos. That's sort of shown by this ice blue band right here. But I'll also point out that if you look at this sort of high energy region for neutrino telescopes and this ultra high energy region for neutrino telescopes, you can kind of see that there are fewer neutrino telescopes that are planned for this gap in energy between about 1 and 100 PeV. And I find this to be sort of interesting because of the fact that these kind of discovery prospects for ultra high energy neutrino observatories is very uncertain, just because we really have not a very good idea of what the neutrino flux is expected to look like at those high energies. And so this is really where I see TAMBO fitting in. So TAMBO is going to have sensitivity to PeV energy neutrinos, which we know for a fact exist because of the observation by IceCube here. So our feet will sort of be firmly planted in this known region, but then we'll also be able to extend up to about 100 PeV into this unknown area of the neutrino flux and characterize whether or not there's this cutoff at higher energies or not. And I think this is sort of a prudent approach because I also point out that if you look at some of these experiments like Grand 200K, for instance, which is shown here in the orange is the most sensitive, these are not small experiments. Grand 200K calls for a radio array that's about the size of the country of France. So these are really big investments. So we really want to characterize the neutrino flux as well as possible, I think, before making these very large scale investments. Okay, so that's one thing that TAMBO can do. So now I should probably actually tell you what TAMBO is before I go any more into things. So yeah, this is an overview of the TAMBO proto collaboration. We're a worldwide collaboration with many members in the United States, also in Canada. Since we're looking at locating ourselves in Peru, of course, we're going to have Peruvian collaborators. Also, we have collaborators in Europe as well as Australia. And then for, I guess, an overview of the actual telescope itself, I like this cartoon because it kind of explains the entire mechanism of action for TAMBO. So TAMBO stands for the Tau Air Shower Mountain-Based Observatory. A little bit of a less contrived, I'll say, description is that TAMBO is a neutrino telescope which is searching for Earth-skimming tau neutrinos and will be located in the Colca Canyon in the Peruvian Andes. So one question you might have is, why are we looking for Earth-skimming tau neutrinos? Why not just look for any neutrinos? Well, it's simply because of the fact that at the energies we're interested in, the Earth is actually opaque to neutrinos. And so we can only tolerate the neutrinos passing through a small amount of the Earth's crust before they interact and are lost. So that's why we have to look for Earth-skimming neutrinos. So the idea behind TAMBO is that we have a neutrino coming in here. If we get lucky, hopefully it'll undergo a charged current interaction very close to the canyon face. When it does, it will produce a tau lepton, which can then exit out of the rock into the space of the canyon and will then decay, creating an air shower. This air shower is then going to bombard the opposite canyon face with charged particles and photons. So this process is, of course, happening all the time naturally. And what we want to do is we want to put an array of detectors that's actually very similar to like cosmic ray air shower arrays on the opposite canyon face so that we can observe this tau air shower, which sort of serves as a smoking gun signal of a tau neutrino. That's the overall idea behind how exactly TAMBO works. So of course, probably a reasonable question to ask at this point is, okay, why are you putting your detector on the side of a canyon? That seems very hard. I agree, it does seem hard. But I think in the end, there's a benefit to it. So another idea that you could have is instead of putting your detector on the side of a canyon, you could just put your air shower array on sort of a flat plane that's next to a mountain. And so now you can see the sort of same air shower signature from neutrinos passing through the mountain, but this sort of has inherently low geometric acceptance, just because of the fact that instead of looking, straight on at this array, you're instead looking at like an angle. So you get penalized by this cosine theta term. So what you can instead do is you can say, okay, well, I'm just going to take the mountain and rotate it so that it's now levitating above, about 5 kilometers above my air shower detector, right? So this is perfect for the physics because we've now maximized this sort of flux that we see through our detector array here. Unfortunately, I spoke to some engineers and they didn't really seem to think that it would be possible to levitate a mountain 5 kilometers above our detector array. So what we have to do is we have to take our mountain, rotate it back down. Instead, what we can think of doing is taking this flat detector array and rotating it instead. And how do you rotate it? Well, you put it on the side of a mountain like this. So this is sort of the idea behind why we want to put the detector inside of the canyon. It's one of the benefits. All right, so to give you an idea of sort of the scale of the observatory, both in terms of like physical size and also, I don't know, physics size, number of events, we expect to observe about 3 tau neutrinos per year if we have 5,000 detection modules. This makes some assumptions like 150-meter spacing of the detectors on a triangular grid. And if we go 3 kilometers up the canyon, this means that the overall array is going to be about 33 kilometers long if we instrument one side of the canyon. If you do both, you can get away with a smaller or the less long array of only about 16 kilometers on both sides. All right, and up to this point, I've sort of been talking a lot about how TAMBO is exclusively sensitive to tau neutrinos, but I haven't really backed that up. So why is it that TAMBO is sensitive exclusively to these new taus? Well, it's because of this air shower signature created by the taus, and this is kind of exemplified in this plot over here on the right. So both these top 2 plots here are sort of looking on the canyon from the top down. They're topographical plots. So brown is at a higher altitude. Blue is at a lower altitude. You can think of it as sort of like a river that's running through the canyon. In fact, there is a river that runs through this canyon. The red here is the tau neutrino or the tau lepton, and then the black is a muon neutrino or muon, mu lepton, sure. And down here, what you see on this plot is the energy of either the neutrino or the lepton, the charged lepton, as it passes through the rock and into the canyon. So at first, we start out with neutrinos. They undergo charge current interactions to create their corresponding charged lepton. What you'll notice is that the tau actually loses very little energy in the rock before it decays into the shower. Compare this with the muon, though, which sort of immediately loses very, very large amounts of its energy into the rock. And so while it's possible for a muon to come out of the canyon face and generate a shower, it will have lost so much energy as it passes through the rock to get to the canyon that the shower that it creates is not going to be large enough for us to see in TAMBO. So this is another benefit of this sort of canyon geometry. It's the fact that the canyon walls are sucking all the energy out of these muons before they reach TAMBO, but sort of leave the energy of the taus intact. It's the same story for electrons, but even more extreme than muons. They're basically stopped immediately. Yeah, so that's how nu tau. As for why nu tau, there are a few reasons. The first reason I think goes back to exactly what I was saying earlier about wanting to do these flavor measurements. So of course, by measuring this tau neutrino flux, we're going to have complementary flavor measurements with IceCube style detectors. But there's actually something I think that is a little bit more interesting, at least in my opinion, that you can do with this tau identification. So I mentioned earlier that if you see a neutrino, unfortunately, it's not possible to say whether or not this is an astrophysical neutrino or whether it's a background from an a background atmospheric neutrino. This is not actually 100% true. It actually is possible with tau neutrinos and TAMBO to determine up to a pretty high confidence if a neutrino is astrophysical or not. So this is sort of for 2 reasons. So first, we can look over here at the right-hand plot. This is the flux of neutrinos that are coming from atmospherics, so essentially cosmic ray neutrinos. And what I want you to pay attention here to is this is just looking at the flux of these different flavor of neutrinos as a function of energy. So if we look at these tau neutrinos in red, you can see that the flux of tau neutrinos as a percentage of the atmospheric component is going to be below 10% over our entire energy range. So the taus only make up a very small fraction of this flux. In addition, you can see that the atmospheric energy spectrum really falls off as you go up to higher energies. So from the combination of these 2 effects, if you see a high energy tau neutrino in TAMBO, you can actually be quite confident that it is a neutrino of astrophysical origin. So I can actually, I guess, pose this statement in a bit more, provocative way, I'll say. which is that every tau neutrino that you see in TAMBO is a new source of astrophysical neutrinos that we discover. Okay, so that's great, but what can you do with 3 neutrinos per year? That's very few neutrinos. And it turns out you can actually do a lot when you combine these results with things like IceCube. So as saying before, this kind of look elsewhere effect in the all-sky search really limits the sensitivities for IceCube detecting point sources. But what if we knew exactly where to point? Well, what we can do with TAMBO is we have these very high purity new tau events, which we know are to a very high probability going to be astrophysical. We can look at those locations in the sky and we can tell IceCube to, point its analysis at that exact point. And so that will remove the look elsewhere effect and greatly increase the sensitivity of IceCube to these point sources. And I kind of want to take it back to the second slide that I showed and point out that this idea is kind of exactly analogous to what I was saying with Neptune. As soon as they knew where to point the telescope to see Neptune, they observed it basically immediately. If you know where to point IceCube analyses in order to observe these point source neutrinos, your sensitivity to them is going to increase basically immediately. I think this is one of the big ideas behind TAMBO. Okay, so to recap, here are the goals of TAMBO. We are looking to determine this existence of a high energy cutoff up here, characterizing the flux by measuring the new tau component, complementary to IceCube-like detectors, and also help discover these new point sources of neutrinos. All right, so that's the big overview. Now I want to go into a few more details of TAMBO. In particular, some of the members of our group have actually been spending a lot of time over the past 2 years working on an upgraded version of the TAMBO simulation. So I'm going to go into that a little bit now. And I think this is also good because going over the simulation kind of gives you an idea of the physics that is going on behind the scenes that make TAMBO work. So when we started out, we had this kind of preliminary simulation shown over here on the right. And there are a number of conservative estimates made just to get a rough idea of the event rate in TAMBO. So these are things like we used to simplify geometry. Before I took a trip to Peru about 2 years ago, I had never seen a canyon in person before, but even I knew a canyon didn't look exactly like this. This is a little bit idealized, I'll say. There's no treatment of the tau energy losses, and then it also used an approximation of the air shower physics, which is all good for getting these sort of initial estimates to see if this is reasonable, but now we'd like to take this a little bit further. So in our updated simulation, what this features is a more realistic geometry. As you can see over here, this is a much more realistic geometry. It's actually pulled from GIS data, so it's going to be very precise. It's a full treatment of the tau energy losses. And then also we're including an air shower simulation with Corsica 8. You can see some of the actual individual particles plotted here on this graph. And I also want to give a shout out to Jeff Lazar and Pavel Zelnin. So Jeff was previously working with us at Harvard. Now he's a postdoc working at UC Leuven, still extremely involved in TAMBO. And Pavel is a grad student who is still toiling away in our group here. Yeah, so I mentioned on the previous slide that we weren't really considering tau energy losses, and part of that was that we weren't considering this process of tau regeneration. So I want to go over quickly exactly what this idea is. So the basic idea is that if you have a tau neutrino passing through the Earth, it can undergo a charge current interaction, create a tau lepton. This tau lepton will travel a very short distance, and remember from earlier, it's only going to lose a very small fraction of its energy. At that point, it will decay, create another tau neutrino, and this tau neutrino will continue transiting through the Earth and can actually be detected by whatever your detector is, IceCube, TAMBO. It doesn't really matter to them if they're seeing the secondary tau neutrino or the original tau neutrino. And so this is actually a process that only happens for taus, just because if you have electrons and muons, when they convert into their charged leptons, they're going to lose all this energy here. And if they convert back into neutrinos, the neutrinos are just going to be, they're going to be too low energy now. They're going to be too subthreshold to observe. So if you include this effect now, this actually results in higher rates than were predicted in the preliminary simulation, because previously these events were sort of just thrown out if they underwent these interactions in the Earth. So these three plots up here on the top show us, I guess, sort of the impact of this tau regeneration effect. So on the y-axis, this is the number of events. This is not physical events. This is from simulation. Really, what I want you to pay attention to is just the change in shape of the distributions is where the physical effect is most visible here. So number of events as a function of energy. And the three different plots look at neutrinos coming from three different ranges of angles. So over here, this is looking for neutrinos that are basically horizontal. In the middle are slightly upgoing neutrinos. And then on the right are even more upgoing neutrinos. And the pink spectrum here is the injected neutrino energy spectrum. And then the purple color here is the energy of the tau neutrinos when they arrive at our TAMBO detector volume. And so what you can see is that these sort of horizontal taus that don't really have to pass through much of the Earth sort of retain mostly their overall initial injected shape. But then if you look at these neutrinos which have passed through more of the Earth, which are more steeply upgoing, the shape of this distribution is actually significantly more deformed, and you actually now get a peak at energies of about a PeV. And so this really has a strong impact on your energy spectrum. I'll also point out the fact that this peak is actually sort of right within the range which TAMBO is sensitive. And so we're operating in an energy range that is, I guess, very favorable to capture these neutrinos, which are undergoing tau regeneration, which will up our rates overall. So yeah, all of this is actually handled in our simulation using the Tau Runner package, which is available on GitHub, open sourced. Yeah, and then one other thing is, as I mentioned, we're now using Corsica 8 to track individual particles. This allows us to get individual particle energies and their arrival times. This is really important to do things like detector optimization studies. You sort of need this detailed information. It also allows you to do neat things like steal IceCube's event display idea and make your own event displays. So again, here the blue to brown is a topographical map. Blue is lower altitude, like the river. Then these different colored circles, redder means that a particle hit the tank earlier, and more blue means that a particle hit the detector later on. So what's happening here is that this shower is coming in and sort of spreading from right to left across the detector here. And something else I'll point out, just because I think it's pretty interesting, is that if you look at this site that we're simulating here, you sort of have this not flat, but smooth face of the canyon here, this kind of notch here, and then a more rugged area over here. Well, if you look at this topographical view, you can again see that we have this kind of smooth face, this notch here, and then a more sort of rugged area over here. And the only reason that I point this out is just because I think that it's very cool that we have this extremely complicated mountainous canyon geometry that has actually been put into a physics simulation. I just think that that's very neat. Okay, so that's kind of an overview of points in the simulation. So what does that tell us? What do we expect to see? So over here on the left plot is predictions for the number of events that we expect to see as a function of energy. So the different colors here represent different flux models. The solid lines represent the updated simulation, and then the dotted lines represent the previous simulation. So we're pretty happy to see the results because essentially what they show is that this initial, more preliminary simulation was in fact a conservative estimate. And for most of these fluxes, it depends on the exact flux that you look at, but we're predicting to see about 3 times higher rates than from the preliminary simulation. Something else that was sort of interesting is, earlier I was mentioning looking at these different flux models, trying to distinguish them in IceCube. Well, what we found is that if you assume that the flux follows one of these models by cutoff, you're actually able to get 3 sigma sensitivity to reject just the sort of basic single power law model in 3 years with only 5,000 modules, which I thought was also pretty nice to see. All right, so yeah, that's kind of an overview, an end of the overview and simulation. My last section, I would like to talk about actually realizing TAMBO. So I mentioned that we were spending most of our time kind of on the simulation. We weren't spending all of our time on the simulation, though. We're also doing some detector development in the lab. So for the detector technology that we're going to use for TAMBO, we're currently planning on either using water Cherenkov tanks or plastic scintillator panels. And I'll point out that both of these technologies are really sort of well-experienced technologies within the field of cosmic ray air shower arrays. And so there's not a huge amount of fundamental R&D we think that we're going to need to debug or work on in order to develop these detectors. More, it's going to be kind of looking at the specific situation that TAMBO is in and adapting these detectors for our specific situation. So these include things like the fact that we have to deploy these detectors in a canyon, which is going to be difficult. Also, the cost of producing thousands of these detectors, as well as timing requirements for TAMBO. These are all things that we're keeping in mind. And so this detector development work is being headed up by Dia Delgado, who is also a grad student within our group. Yeah, and then also we've been involved a little bit in some outreach to communities in Peru, sort of broadly. So we've met with kind of we've met with the academic population for one. In fall of 2022, we took a trip to Peru. We held a workshop at sort of the university in the city closest to the Colca Canyon. It's a university in Arequipa. And then also during this trip, we met with national officials as well as some more local officials. So we wanted to kind of interact with the community a little bit, see what their perception of the project was. Fortunately, it seems to be generally positive. And we also wanted to take an opportunity to visit the site. So just to give you an idea of this, so Arequipa, which is the town this workshop was held in, which is actually off the bottom of the slide somewhere here. From Arequipa, you drive about 3 hours north on this highway to get to Chivay, which is sort of the largest town in this canyon area. It's a town of about 5,000 people. From there, you drive about an hour out this highway to get to Caminacande. Once you get to Caminacande, you then go off-road and start driving along the edge of the canyon for about another hour until you get to this sort of site in the canyon that seems to be kind of the most promising for TAMBO. So this is, really extremely remote, takes a long time to get to. It's very rugged. You have to have a very nice truck and a very capable driver, which fortunately we did. Um, but there are fortunately sort of promising closer areas that you could use for a smaller test array, which is something that we're thinking of doing now. And I guess one sort of thing I wanted to share with you also was the reason that I wanted to go on this trip was because this canyon is very large, right? I was hoping to kind of get a better idea of just how large the canyon was. So I sort of showed up here, got out of the car, walked over the edge, and looked out at the canyon and was sort of just like, wow, this is very big, much larger than anything else I had ever seen. That it's really seeing it in person doesn't even help you to contextualize just how large it is. And I actually figured out later on that it's kind of easier to get an idea of the scope of the canyon just by looking at things on Google Maps. But then you don't get to take a trip to Peru. So there are benefits and detriments. And yeah, one thing that I'll just use to wrap up this section is also that you might have been noticing in some of these photos that this place is not like some sort of like uninhabited, desolate wasteland or something, right? It's like there's people that live here. There's arable land. There's people that do farming. It's very sparsely populated, but there are people that live here. And so something that we want to make sure is we want to make sure that this project is really being sort of embraced by the local community and not just tolerated. So this area is sort of it's a very mineral rich area, so there's a lot of mining in the area. And I won't say that the miners are really sort of looked upon super favorably by the local population, is my understanding, but they are sort of tolerated or accepted because they do provide, well, they're legally required to provide infrastructure for these towns. So they do get some benefit. But what we want to make sure is that we're not really acting as one of these extractive industries where we're just being tolerated. We really want to put in an effort to be accepted within the community. If we're not wanted here, we're not going to be doing this experiment here. This is a requirement for us. So something that we've been doing is kind of as a first step, I organized this workshop that we had at Harvard, which brought together physicists from projects like Hawk and Pierre Auger, sort of similar scale projects that have also interacted with local communities, along with social scientists from Peru, and also some national officials in order to sort of just start this conversation. And this is kind of going to be an ongoing project. And then here, this is essentially my last slide. So just what do we have in terms of timeline? So right now, we'd like to deploy a smaller R&D array within the year. If we look at the year 2027, and and use this for the STAR deployment. If we deploy our detectors at the same rate that the PRJ observatory deployed their modules, we can deploy about 1,500 per year, and that means we'll have a full detector sometime in 2033. And kind of an interesting feature of this timeline is that if you look at these different colors here, these different colors correspond to different fluxes. And what these bands represent are actually the 68% confidence interval band for when we'll see our first event. So you can see that for most of these fluxes, all except the most pessimistic, we actually expect to see our first new tau event in fewer than 2 years with only 1,500 modules. So this is something that was very exciting to see. Yeah, so I'll just summarize quickly. So TAMBO, our goals are to kind of bridge the gap between high energy and ultra high energy neutrino telescopes. We also want to enable the discovery of hidden neutrino sources with our very pure sample of astrophysical neutrinos. There's this fully featured simulation nearing completion. Be on the lookout for a paper soon. The development of prototype detectors is underway. And then right now we really are sort of just person power limited in terms of what we can do. So if you're interested in getting involved, please reach out to either me or my advisor, Carlos, and we'd be happy to talk with you. And yeah, thanks for your attention. I'd be happy to take any questions that you might have.
Super. Thank you very much for the talk. It's been very interesting, very nice, and very nice pictures too.
Thanks.
So we're open for questions. Oh my God, we already have questions on the YouTube chat. Usually there's like a delay between the end of the talk and the questions, but I guess we can start with the YouTube questions. So there's a question from Adrian asking, do neutrinos undergo gravitational lensing around point sources? Is that something that could be disentangled by future experiments with good directional reconstruction?
Oh, I mean, in principle, they should. My feeling is that anything in the near future, just to give you an idea, is so on the sky with IceCube and some future neutrino detectors, we're sort of operating at the level of like order 0.1 degree resolution. So it's still very coarse, I think, in terms of doing things like distinguishing lens neutrinos from behind like an active galactic nuclei or something like that. Compared to optical telescopes, the resolution is still very poor. So for TAMBO in particular, just to give you an idea, sort of what our target is that we'd like to get resolutions that are about like a
Sorry,
degree or so. Hello.
sorry, we're home.
No, no.
Okay, yeah, no, please go on, he'll behave.
Oh yeah, that's all, I think.
Okay,
There
sorry.
was a follow-up.
There was another question. Would it be sensitive? Are you sensitive to the hadronically decaying taus? So I think you are, but
Yeah. So the hadronically decaying taus are I think it would be the primary ones that create these showers. So we should be sensitive to those as well.
okay, good. So any other questions from the? Sorry about the interruption because I'm home. Any other questions from the people here at Zoom, from the other organizers? Maybe Roberto or Nicolas has got a question.
Yes, I have a question for Will. Very nice the talk and very nice the TAMBO experiment, I mean observatory. So I was wondering, is besides the objective to measure taus neutrinos, the same detector can be purpose for other type of analysis, kind of shower, atmospheric shower for gamma rays or something like that, on top of the also to analyze the tau plus other astroparticle signatures, not related with the neutrino, but that can also be done with TAMBO because of the location and everything of the sky.
Yeah. So something that we're I guess we have thoughts that it might be useful to do, but we haven't really had time to look into it since we don't have I guess enough people to just do this right now, is that essentially TAMBO is like an air shower array, right? It's just on the side of a mountain. And so something we think could be interesting is that since most of these air shower arrays are on sort of flat planes, having this air shower array that's on an inclined plane could actually allow you to do things like looking at a shower kind of as it develops going down in the canyon. And so this is, I think, kind of would be a unique geometry for cosmic ray measurements. There have been some people who are, they're actual cosmic ray physicists. I'm not actually a cosmic ray physicist. None of us are. We kind of just pretend to be to understand these showers. But they're actually kind of interested in looking at possibilities of looking at TAMBO with that. So that's sort of one thing that we've looked at, or an example of one thing.
Sorry, I was muted. So, and the other question that I mean, maybe is kind of technical because of since the main city is quite, let's say, far from the site location. So I was wondering how it's planning kind of to manage the data output that it will produce the TAMBO, let's say. I mean, why I'm asking that, because here in Chile and also in the south of Peru and part of Bolivia, there is a tentative site for a gamma ray observatory called SWGO. And one of the hardest part is to see how we are gonna, or how the data is gonna be pushed away from the site to be processed elsewhere. Yeah. This is the kind of, because the remote location, that's the question.
Yeah, so maybe this is not what you want to hear, but we're big fans of putting SWGO at this site in Peru because it's actually kind of close to the site for TAMBO. It's still like many miles, maybe order 100, well, okay, I'll say 100 kilometers. Maybe that's more natural units for this environment. But I think that, yeah, the data transfer is something I think will be challenging on a few levels. We haven't really thought much about data transfer from sort of like the full observatory out. Maybe you could think about doing something like some sort of satellite transfer like Starlink. That's something that we should probably look more into. One thing that we have thought about a little bit is about data transfer between like individual stations. So these things are going to be stationed like order 100 meters apart from each other. I guess for a few reasons you wouldn't really want to run wires between them. I don't think there's sort of like the ecological perspective, which is that I don't know. I don't have any. I can't back this objectively, but I would feel kind of bad like running wires all over this environment personally. There's also the fact that if you do that, probably it's going to be a decent amount of work to make sure these are kind of robust against environmental conditions or things like that. And then also the fact I would kind of be concerned that if we were putting a bunch of like copper wire out there, people might try and take the copper wire. So what we're thinking about is actually trying to develop some sort of system where we could transfer all of this data wirelessly. So something that's like under active development now by one of the groups in Peru at UTEC is that they're working on one aspect of this, which is like a timing system, which instead of like, I don't know, a white rabbit fiber optic sort of thing, is instead going to create like beacons where you have like a central timing station that sends out like a timing beacon to all these individual modules and does the timing that way. So that's something that we're sort of starting to think about. But as far as like, large scale, we have hundreds of gigabytes of data. How do we get it out of this canyon? I think that probably that requires some more thought.
Okay, thank
you.
So any other questions? Let's see if there's anything on the chat. Oh yeah, we have more on the chat. Let's see. So there's a comment by Chantal Desai saying that Chris Quigg and Irina Mocho have a paper on lensing of neutrinos of around 2005. But then there's a follow-up question asking if HIRES or Pierre Roger, if those observatories are also sensitive to tau neutrinos.
Yeah, so I'm pretty sure that I think it's Pierre Auger it was that did this kind of analysis that I was talking about with the let me jump back to it. This sort of thing, which is that they were looking for neutrinos from a mountain, or it may have been that they were looking for actually Earth skimming neutrinos that were going slightly upwards. I can't remember which one of those it was, which experiment did that, but sort of in any case, the result was that they weren't able to see any of these neutrinos, and I think a big factor was that regardless if it was this mountain setup or if it was looking for kind of very just barely upgoing Earth skimming neutrinos, um, the geometrical acceptance is going to be very small just because just from geometry. So they are not observed in those analyses.
Right. Super. So let's see. Let me
Maybe
ask one.
maybe
Sorry, yeah, go
also,
ahead.
yeah, sorry, I didn't mention this at all because I was kind of limited for time, but something else I'll point out is that another feature of putting sort of TAMBO in a canyon that's nice is that essentially if you think of yourself sort of like standing, I guess I'll say by this mountain, you can only see the sky that's behind the mountain, right? Because you're looking for this kind of interaction. So you're kind of limited in your field of view also. But if you instead think about going down into the canyon, now when you look out, you sort of have this entire rock wall in front of you. So you can see the sky behind this rock wall. You kind of greatly enhance your field of view in addition to kind of this detector acceptance. Now, of course, when you go further out the sides, then your detector becomes kind of, smaller because of this geometric effect. But overall, you can see more of the sky with this.
Super. And
Yes, I just wanted to
that
out
then
too.
the question is, I mean, I understand you have the good views and the better pisco sour in Peru, but why the Colca, right? Why like there are canyons elsewhere in the world, right? So what's the particular feature of the Colca Valley?
Yeah, so there are a few things. Something that I think is kind of particularly interesting from like the physics perspective is that, well, I was saying earlier with IceCube, how well you can distinguish these tau events depends on how long the tau lives for, right? So it's kind of an energy dependent thing whether or not you can see the tau, because that determines the length the tau travels. Well, here actually the spacing between the sides of the canyon kind of determines what sort of energy range you can do with your physics. Because if you have like taus of about a PeV, they'll travel something like 50 meters. So if your canyon is too thin, then your air shower is not really going to have a chance to to develop fully. And so it'll be kind of hard to distinguish that between it'd kind of be hard to distinguish that from other backgrounds that you might have. I think it'll also probably make your timing a little bit more difficult. If the canyon is too wide, then what happens is you actually start to lose particles just because all their energy gets sucked out from interactions in the air or from, well, yeah, essentially from interactions in the air. And so it's kind of the geometry of the canyon is sort of setting the physics that you can do in this interesting way. Okay, so then why Colca in particular? So one is I think that there's sort of just general interest in the community to do it here. There are a few other places. So I know that like there's some sites in China which have canyons, which might be suitable also. There's the Grand Canyon actually, in the US. I don't think that the Department of the Interior would be too keen on us putting a neutrino detector in the Grand Canyon, though to be fair, nobody has actually asked yet. So in principle, really it could be kind of any canyon that meets these physical requirements. Um, I can't promise that we've done an exhaustive search of all these canyons, plus that's, you can't, there's no Wikipedia article for canyons that are deeper than 3 kilometers and also have a spacing over, some amount and which are also more than 10 kilometers long or something like that. So if anybody has any other ideas for canyons, they could be entertained. But right now, I think it's just sort of kind of political interest and then also scientific interest in Peru.
Mhm. Super. Super. And the modules, what is the expected size for each module? Because of course you were mentioning like not wanting to have the detector there, but of course that depends if how many you're putting, how large they are.
Mhm. Mhm. Yeah, so I mean, what I'm showing right now, these panels are actually probably larger than what we would want to use overall. So I guess first I should say is that now that we kind of finished up the simulation, we're moving on to wanting to detector optimization, and that'll include things like exactly what the size of the detector should be. So these detectors that we're building right now are actually slightly larger than what were looked at in our original white paper. Uh, the reason for that is because we got some surplus supplies and get these for free. So, that was nice. But moving forward, we're going to want to start kind of make them a little more especially for TAMBO. So for instance, like well, this wasn't exactly your question, but just as an example, like right now the readout on these sorts of panels is being done with a SIPM that is at the end of this bundle of fibers, which is run through each of these plastic scintillators. This won't work for the final version of TAMBO just because there's some intrinsic timing uncertainty based on where your particle hits the detector here. And that intrinsic timing uncertainty is actually larger than what we can tolerate. So, a smaller detector will help that somewhat, but yeah, exactly what it looks like we first need to determine, I think, from the simulation, the detector optimization to simulation.
Okay. Great. We have some other comments by Shantanao Desai. So if the question is if this can be done near CTIO in Chile, where there is already a scientific infrastructure due to LSST, the mountains near Serena. But I understand that we already cleared that it's the Pisco Sour, right?
Yeah, I mean, so the other thing is that like half the people working on this are from Peru, so you're gonna have to, that's gonna be a hard sell for them. But to actually answer the question, maybe I'm not really familiar with the geography in that area, but take a look.
Yeah, it's a thing of the width again, I guess. No.
Yeah, and depth is also a big thing because if it's not deep, then it sort of has to be very long linearly, which is, I think, in a sense, it's kind of more desirable to keep it compact and unobtrusive as possible.
Right. One final question from my side is so you mentioned that in your simulation you would have the electrons absorbed, the muons would be attenuated, and then the taus would go through. But that depends on the place where the interaction happens, right? If this is close to the edge of the mountain, then there's a chance that the muon is not attenuated enough, or maybe the electrons do escape and generate an electromagnetic shower. You contemplate this kind of situations?
Yeah, right. So it's possible that there's like, I don't know, a small pebble sitting on the canyon face, and that's where the interaction happens and creates a muon, where it'll lose basically no energy, right? So that's possible. It just happens very rarely because I guess it sort of has to do with the tau length in comparison to sort of the characteristic length of muon energy losses. And I think it's just the fact that you kind of have to get, I guess we'll say, unlucky and have a muon, which happens very close to the canyon face. And so that's only going to be, I think this was looked at in the original simulation, and the number of times this would happen is like once out of 20 tau neutrino events. You could get a muon that showers. But then, I don't know exactly how this is going to be affected in the the new simulation, I would expect that it would get better since we were increasing the overall number of towels that we have in our detector. But this is something that is on our list to check going forward.
I see.
Yeah, you
I
can
see.
get unlucky and have these sorts of showers, but it's just kind of a probability thing that you win by having very.
Yeah, but there's no. I mean, I thought that the muon wouldn't generate a shower, right? That it would just like get like a
Yeah,
signal that doesn't spread out so much.
so most of the time, it will not create a shower, is my
Mm.
understanding. But there are some cases where it can just stochastically happen to dump a bunch of energy, all at once, and that can create a shower. Now, perhaps there's ways to do like characterization of the shower that allows you to distinguish that from different, a shower created by a towel. This is why we want to work with more cosmic ray people so we can figure out if that could be done or not.
Mhm. Okay, so I don't know if there's any other questions on the chat, the YouTube chat doesn't have any update. I don't know if any of the other coordinators would like to ask something. I think we're good. Okay, so that's that. Thank you very much, Will, for the fantastic talk and your fantastic answers. And please, everybody, stay tuned for this interesting experiment. So before we say goodbye, let me remind everybody that in 2 weeks' time we have Andre Frankenthal giving a talk. So please be aware. Okay, so that's it. Thank you very much, Will, for being here. It's been great.
Yeah, thank you.
Bye, everybody.